Hi, thanks so much for stopping by our lab's research page for ORS 2023. My name is Sam Mircoff, and in this video, I'll be giving a brief overview of my work. Let's start with some background. It's known that bone changes during postnatal growth in order to accommodate for the increased loads that bones experience as we begin to move around and put new mechanical stresses and strains on our skeleton. Now, a prominent example of this is the bicondylar angle seen here in the femur. Looking at figure 1, we can see that at birth, the bicondylar angle is essentially 0. This is a straight line. However, as we begin to ambulate, asymmetric loading at the plane of the condyles causes the medial aspect of the femur to grow longer, or to grow faster and therefore longer than the lateral side of the bone, which ultimately results in this bicondylar angle, which is characteristic of the femur. It's notable that this angle is absent in the case of non-ambulation. Now, the sensitivity of formation, resorption, bone modeling to the local mechanical environment during growth isn't as clearly understood. We know that longitudinal growth is load dependent. However, the particulars of load dependence on radial growth, which is depicted here in this image, isn't as clear. That brings us to our primary objective of this study, which was to determine the degree to which variation in periosteal formation rates is explained by the local mechanical environment. That brings us to the methods of our study. Our data set consisted of computed tomography or CT scans of 3 different foals ranging in age from 7 to 47 weeks old. The scans were taken at 15 unique time points, which is demonstrated broadly with this image, specifically taken of the first phalanx, which is this small bone depicted in this image. We limited our study to a maximum time interval of 12 weeks, which gave us 22 unique pairs of data to work with moving forward. Next, because we set out to determine radial growth as it relates to mechanical signaling, it was important that we used a fixed reference point in our data set so that we could effectively compare our growth. In order to do so, we looked specifically at cross-sections, which contains the nutrient foramen, which is shown here in this image. The nutrient foramen is this really small channel through the cortical bone that essentially grants vasculature an entryway so that it can feed and nourish the bone. Using a MATLAB code, which was adapted from a previous study in our lab, we used hydroxyapatite phantoms in order to segment just cortical regions of our cross sections of the CT scans. We did this because these regions is where we found the periosteal border. Then we used MATLAB to identify the centroid of each scan, and we calculated the distance from the centroid to the periosteal border at 100 distinct points around the periosteum. By overlaying the centroid of 2 cross-sectional scans for each unique time interval in our data set, we were able to calculate periosteal apposition over time. You can see the differences in periosteal distances here in this image. To identify the mechanical signaling in our scans, we used subject-matched FEA models, finite element analysis models, of the P1, which were performed in abacus and based off of the joint contact forces experienced during a normative trotting gait. Once again, this code was adapted from a previous study done in our lab. Using the FEA models, we were able to identify the local strain felt particularly along the periosteal border, as I mentioned earlier, which you can see in this figure. Finally, we divided the periosteal apposition and the local microstrains into 4 regional quadrants across the AP axis. You can see here we have the anterior, posterior, lateral, and medial quadrants. And for each of the metrics we calculated, we averaged them per quadrant. And we did so across every unique time interval. Growth rates were calculated using this equation seen here, once again using the periosteal apposition divided by the time intervals calculated, and the amount of growth rate explainable by local strain was calculated using the marginal R-squared value, which I'll touch on next. Taking a look at our results section, you can see that we first compared the regional growth rates and the average mechanical signaling felt per quadrant, and we did so using Whitney-Manu paired t-tests. We used this specific t-test after checking for the normality of our data. From the box plot shown, focusing first on average growth rates, you can see that we didn't find any significant difference in growth rates across all 4 quadrants. The median growth rates across each quadrant fell within actually a pretty narrow range seen here between 0.11 and 0.13 millimeters per week. Now, it's important to note that we discarded all values less than 0.1 millimeters per week, and we did so due to the resolution of our CT scanners limiting our ability to realistically calculate anything smaller or more detailed. Looking at the local microstrain, on the other hand, we found that the strain felt in the anterior quadrant was significantly different and much lower than the microstrain felt across each other quadrant, respectively. You can see that the highest mechanical signaling experienced was in the medial and the posterior quadrant, and the lowest, once again, in the anterior. Now, looking below at the relation between growth rate and mechanical signaling, we first created a linear mixed effects model using the microstrain as our fixed effect and the subject, or our foals, as the random effect. And after doing so, we found that the local microstrain explained roughly 10% of the variation in growth rates. This, you can see, was calculated using our marginal R-squared value. Now we can take a look at our findings and key takeaways from this study. Due to our relatively low R-squared, we concluded that the range of loads experienced during non-stressed trotting gait may simply have not been enough to result in morphological change in the diaphysis. Again, we focused specifically on the nutrient foramen, or the cross sections which contained it, which happens to be within this region of bone. As it's been shown that bone growth is load dependent, it therefore follows that the mechanical strains that we found in our data set, ranging from around 175 to 650 microstrain, may indicate a lazy zone of strain stimulus, where mechanics is simply not strong enough to result in any notable significant growth. Of course, more work is needed to confirm this finding. I've mentioned previous work in our lab a few times throughout, and that work is particularly relevant to our findings, as you can see that they found relatively uniform bone accrual in the diaphysis of bone with regards to weight of foals as they aged. However, they found distinctly different bone accrual rates as you moved more distally in the bone, closer to the growth plate, as loads may be more variable and higher in this region. This would be an interesting area to extend our investigation of load-dependent morphological change in future work. Since our study focused particularly on bone growth as it relates to local microstrain, it remains to be seen if any other signals like strain energy density or strain rate, metrics that are more dynamic, may be more correlated to growth patterns in the diaphysis. Limitations of our study are that the models only included microstrain and not effects of dynamic loading, once again, like strain rate. Another major limitation is that our CT resolution limited our assessment of growth rates only to those calculated to be greater than 0.1 millimeters per week. Taking it as a whole, we found that mechanical loading during normative gait was minimally correlated with changes in regional radial growth rates. This is significant because our findings suggest that periosteal formation in the diaphysis may be controlled by different mechanobiological cues than axial growth. I would like to acknowledge the Morris Animal Foundation for funding this work, and I would also like to thank you for your interest in my poster today. Please feel free to find me at the conference or send me an email, and I'll look forward to answering any questions you may have. Thanks.